Ladies and gentlemen, we will start this conference. So it's my pleasure to welcome you here at the University of Geneva, and more precisely at the Faculty of Science, for this late afternoon conference on innovation. And it's also a great pleasure to welcome Professor Shoseyov from Hebrew University from Jerusalem. And it's also the occasion for us to underline that we have a strong collaboration with the Hebrew University of Jerusalem, and it's even one of our strategic partners. So we are pleased to welcome you for this innovation event of today. So innovation is important for universities, and this is why at the University of Geneva we have a technology transfer office, which has been created 20 years ago, and also recently at the Faculty of Science, the Science Innovation Hub, in order to develop great ideas from fundamental research which are done here at the University of Geneva. And innovation, it's not only technical innovation, but it's also, and I want to underline that, it's also social innovation. So this is why it is important at the University of Geneva, which is a comprehensive university, and both technical and social innovation are important because it will help us to face all the big challenges we have to face in our modern society. So, without any further delay, I will give the floor to the Dean of the Science Faculty, Professor Jérôme Lacour. So, a nice evening to you.
Thank you, Stéphane. It's really a true pleasure to be here tonight to welcome Hebrew University and the friends of Hebrew University, because it's really a true partnership today that has sealed actually this possibility to welcome Oded. Oded, thank you so much for being here in Geneva today and participate not only to the event tonight, but also to really interesting discussion with faculty members. This we could see that there is a need for dialogue, there is a need to learn from each other, and this was actually a great opportunity. The Faculty of Science is very proud to be a faculty of fundamental research. Yes, fundamental research. We are very, very strongly on our strong scientific basis. We want to do program which will progress actually blue sky research in the sense of blue sky has really fundamental ideas. Yet, like many institutions in Israel, we are also proud to seize any opportunity that we can have to actually develop an economy based on really rationals and wisdom and science. So, this year, as you may have seen for a few months or so, we've been very proud in Geneva at the Faculty of Science to welcome not just one, but two Nobel Prizes in physics. And the topic could not be more fundamental. Extra solar planets, exoplanets as we call them nowadays. At the time, as Michel Mayor likes to say it, there were 6 or 8 people working on the topics. Like maybe 3 or 4 teams of 2 people, a professor and 1 PhD student. Okay. And with that now, this has become a huge topic of more than 3,000 people working on this, and a lot of also technology associated with it. I cannot count the number of satellites that are going to be actually sent in space in order to really study these questions. But satellites like Cheops, which will be sent normally, don't hold me for this because there can be around, let's say, December 17, are actually true satellites based on Swiss technologies. And to study really fundamental questions, you need an economy and you need companies, you need really like investors who will actually really give you all the tools to be able to develop such actually really important technologies. But those in a way are some of the tools which are, let's say, more classical. A lot of the other tools, a lot of the tools of the 21st century will come probably from really bottom-up approaches at the universities. And through these actually ways of thinking for innovation, we couldn't really dream of a better speaker than Oded today. And I don't know, probably we will have an introduction and we'll summarize actually all the things that Oded has brought to actually Hebrew University. And we think this is actually a good model. Yet at the same time, we decided to seize the opportunity today to show that we can also try at the University of Geneva to put also the ecosystem actually of creation in very positively. And today will be the inauguration, what we call also ourselves a science innovation hub. We learned that there is also a hub at Review University, another thing that brings us together. So if we can keep on sharing a lot of the things together, we'll be very happy, Oded. Okay. This Science Innovation Hub is actually hosted at the Faculty of Science. Our mission is to strengthen support for technology transfers and creation of startups based on technology from all disciplines of the Faculty of Science. This is essentially a pre-incubator, and this is really important, and where we have office and lab spaces, and of course coaching. Coaching is going to be a major role, of course, for this platform. The idea also is to create a bridge between incubators, traditionally in Geneva, Fongit and Eclosion partners, technology transfers, laboratory of advanced technologies, GCC, Genius, and I'm very happy to see many friends from this institution here, and also trying to create actually a relationship with experts, patent attorneys, investors, companies, etc. The eligibility to join the pre-incubator are based on research projects involving the Faculty of Science. Doesn't mean that it has to be from the Faculty of Science. We want a relationship, we want a tie with these projects. They have, of course, to be disruptive but sustainable business ideas. This is the ideal. And we want motivated entrepreneurs. And from the University of Geneva, the HEC, and HUC, and every good program with the Faculty of GSM, and I salute the Dean of GSM, Marcello, would be great in order to create these entrepreneurs. Okay. The benefits, if you are accepted actually to the Science Innovation Hub, will be office and lab space for 6 months, renewable, of course, based on actually a committee will decide on whether the contract will be extended, but usually it should not be more than 1 year because other structures should be there actually to take over, and more importantly, we should leave some space for new projects to come at any given time. Prefers at first to the infrastructure of the university, access to the innovation ecosystem, of course. So within this was created essentially less than 4 months ago, actually formally. We have already 4 actually startup projects or pre-startup projects. Aperi, a drug delivery platform for the development of topical eye drop formulation for the delivery of biologics such as anti-VEGF. Bacterial biocellulose also. The aim is of this project to develop application based on very high purity, biocompatible, biodegradable bacterial biocellulose. We have projects on protecting the grapes with laser technologies, and we will actually, for some of these projects, hear their part of their founders, scientific founders for this, for real-time and high spatial accuracy detection of spores like mildew, okay, allowing the winemakers, very important in Geneva and elsewhere, of course, to treat very gently their grapes, combination of laser technology and AI to recognize the spore in air. And the latest project of essentially today, because he's joining actually today, is Fluorosphera, 3D cell culture methods to allow for the simultaneous measurements of several biological activities of several cell types in cold culture. And one of the ideas, of course, is to be one of the R in 3R research for the reduction of animal testing. Okay. With that, okay, I hope I created hopefully enough excitement to welcome Oded. And please really join us actually today for Nature's Gifts, Materials for the Future. Professor Oded Shoseyov, please.
Thank you very much. So how do I switch to my program? It is there. Well, good evening. And first, thank you very much for having me here. I'm really excited to be in this vibrant, exciting place. I thank you for giving me the opportunity to come to tell you about some of the things we've been doing in my laboratory at the Hebrew University. And a special thank to the friends of the Hebrew University that made it possible for me to come here. So before I start, I'd like to try and convince you that we are on the verge of what I call the plant age. But really before I start my presentation, I would like to quote the former Minister of Oil of Saudi Arabia, who said something very smart. He said that the Stone Age did not end for lack of stones. And the oil age is going to end long before it runs out of oil in our wells, and I think for a very good reason. And that is because biomaterials are so much better. But we shouldn't criticize our scientists for not producing a really good synthetic material from oil for a simple reason: we didn't have much time. 200 years of modern chemistry, or maybe 300 years of from the Industrial Revolution, is not enough time to make really good materials. While nature had 3 billion years to develop some of the most amazing materials that we wish we had in our possession. Yet, our orthopedic surgeons, they love to glue and screw synthetic materials in our body, and I don't think that this is a great idea. And why is that? Because synthetic materials fail. Many times they fail because they're not strong enough, just like this plastic fork. But other times they fail because of other reasons, because synthetic materials can be very strong, but their biomechanical properties do not really fit their surrounding tissues, and that's when they fail. But the real reason why it's not a good idea to introduce synthetic materials into our body is because in nature, things are done differently. In nature, there is no one that takes my head and screw it into my neck, or take my skin and glue it onto my body. In nature, everything is self-assembled. Every living cell, or every living organism, and it doesn't matter, it can be a fish, or a plant, or an insect, is composed of cells, and the cells contain DNA. And the DNA encodes for these nanobio building blocks. Many times there are proteins, other times there are enzymes that make other things like polysaccharides or fatty acids. And the common feature of all these nanobio building blocks is that they don't need us. They recognize each other, self-assemble into scaffolds on which cells are growing, proliferating, organizing into tissues. The tissues are organized into organs, and the organs together, that's the organism, or life, if you like. So we at the Faculty of Agriculture, in my laboratory, about 15 years ago, decided to focus on probably the most important nanobiomaterial for us, for human beings, and that's collagen. Now, why collagen? Because collagen accounts for about 30% of our dry weight. We have nothing more than collagen, except for water, in our body. And I'll give you a few examples. Bone is about 50% collagen, 50% minerals. Our skin is about 70% collagen. Tendons and ligaments, close to 100% collagen. So I always like to say that anyone who is in the business of replacement parts for a human being would like to have collagen, because that's the building block. But admittedly, 15 years ago, when we just started our research, there were already in the clinic more than 1,000 different medical implants, all made of collagen. Simple things like dermal fillers to reduce wrinkles, augment lips, artificial meniscus, bone grafts, even leaflets of heart valves, all made of collagen. Well, you should ask me then, why bother? Why did you start the research? Well, the reason was that the source of all their collagen products up until recently was dead bodies. Dead pigs, dead cows, and human cadaver. So that's not a very safe source, because they all harbor human pathogens, like viruses, prions, mad cow disease, you name it. And in fact, already in 2007, the FDA made an announcement asking the companies to start and look for better and safer alternatives. So that's exactly what we did. We cloned all the 5 human genes from human that are responsible to make human collagen. So these are the 2 structural genes, the collagen alpha 1, collagen alpha 2, and then the 3 post-translational modifying enzymes, the P4H alpha, P4H beta, and LH3, which all required for the decoration of the collagen to make it a functional, fully functional molecule. And all these 5 human genes were introduced into a single tobacco plant So now the plant can make human collagen. So the technology was mature. Today in Israel, there is a company called CoPlant. And in Israel, we grow about 25,000 square meters of greenhouses all over the country, from the upper Galilee, in the middle of the country, in the southern part of Israel, where the farmers receive from the company these small tobacco plants. It looks exactly like a regular tobacco, except that they contain 5 human genes that tells the plant how to make human collagen, because plants don't make collagen. The farmers grow the plants for about 50 to 60 days. We harvest the leaves. The leaves are transported by cooling trucks to the factory where we start the process. Now, if you ever made pesto, you know how to make collagen. It's just a bigger food processor. You crush the leaves with some buffer, get the juice, concentrate the protein, and then the protein is then transported, frozen into clean rooms in the science park in Rehovot, across the street from my university, where we do the final purification. And the end result is collagen, which is identical to what we have in our body, except that it's more safe because plants do not harbor human pathogen. And in addition, it's a higher quality because it is not extracted from old used tissue. It's a brand new collagen. And from that collagen, we make different medical implants. And we have already 2 products that already completed clinical trials and reached the markets in Europe and in Israel, and now also in the Far East. And I'll share with you maybe one of them. So the first indication we were after was a flowable gel for diabetic foot ulcer. Now, diabetic foot ulcer affect a quite significant amount of people in the world. Diabetes in general is epidemic. More than 400 million people suffer from diabetes. About 20% of those will experience at least once in their life a diabetic foot ulcer. As a result of that, some are going to lose a toe or the entire foot. In fact, 1 million amputations a year. So every 30 seconds, someone in the world is losing a lower extremity. So this is the product. What the doctor is doing is debribing the dead cells, or remove the dead cells, and then inject the collagen into the wound bed. Now what happened is that the live cells in the periphery of the wound, they recognize the collagen because that's their natural scaffold. So they attach to the collagen via special receptors called integrins and get a signal, tell them, hey guys, you're on the right spot, start to proliferate. So that's exactly what they do. They proliferate and they grow a granulation tissue. And once this tissue reaches the level of the surface of the skin, the keratinocytes start to grow and close the wound. So that product already reached the market. I would like to share with you one tough case, actually from Italy, from Pisa. That gentleman here on the left experienced a very deep wound, goes all the way to the bone, and you can see starting to develop gangrene. So typically 2 years of different treatments that ended up with no cure. And a single application of the human collagen after debridement, you can see on the right-hand side 3 months later, full recovery. That's another case. It's a pressure ulcer. Day 0, 15 weeks later, but note on the left-hand side, in fact, the wound was totally closed after 5 weeks. So that's quite nice and encouraging. But we wanted to take it further and to make really strong materials because, in fact, collagen in our body makes tendons and ligaments. So using classic textiling technologies, wet spinning technologies, which are used by the textile industry, we've been able to take collagen, this human recombinant collagen producing plants, and make liquid crystals and spin fibers. Now, these fibers, after drawing, in fact, were 6 times stronger than Achilles tendon. So remember these fibers, because I'll get to that later on. But now we were really excited about plants, and we said, hey, plants are really great, and they can make really complex proteins. And so we asked ourselves, what's the next thing we want to do? And we decided to focus on biologic drugs. Now, why biologic drugs? Because first of all, they're really excellent drugs, because they go to the target. and they have very few side effects compared to small molecules many times. But here's the problem. They're very, very expensive. To give you one example, Humira, which is anti-TNF-alpha, that is indicated for autoimmune inflammatory disease like Crohn's disease and rheumatoid arthritis. Cost per patient per year is $35,000 US. That's $100 a day. Result is that only 1 out of 1,000 people in the world that would like to enjoy Humira can afford it. So the question is, why is it so expensive? So many of you may say, well, there are patents. Well, there's no patents anymore. They lapsed. Then maybe no competition. Well, there is competition. In fact, 2 American companies, one AbbVie, another one Amgen, make Humira, and another 3 companies, among them one Indian. So how come the price didn't drop significantly? Well, the reason is cost of production. The way today these biologic drugs are produced, humanized antibodies, is by mammalian cells. So mammalian cell culture is very expensive system because it requires these very sophisticated bioreactors. The media is very expensive, clean rooms, utilities, so all that costs a lot of money. So he said, hey, but this is a protein, so it has genes that encodes for it, so let's clone that and stick it into a plant and put it in a greenhouse and produce it at the cost of lettuce or tomatoes. So that's exactly what we did. So now the question is it enough? Well, unfortunately not. Why? Because the purification is also very expensive. Just to give you a feel, today the way the industry does it is with a special kind of column called protein A. Protein A is another recombinant protein that has a very beautiful feature. It has the ability to affinity bind the tail of the antibody. It's a place called the Fc region. So what the people do is they produce this protein, immobilize it into these nice beads, fill this very big column, flow from the top the mixture of everything, and then the protein A binds only the antibody, everything flows through. Once everything flows through, they change the pH, and that releases the antibody. So it's beautiful technology, except very expensive. 1 liter of that column costs $10,000 US. So again, very expensive. So we said, hey, but protein A is also a protein, so it has a gene. So what we did now, we made a trick. We took this protein A gene, we fused a cellulose binding domain, and then stick it also into the plant. So now when we crush the plant, what happened is the cellulose binding domain binds to the plant cell wall. The protein A binds to the antibody. And then we squish it and we wash it. Everything flows through except for the antibody. Change the pH, and voila, we get the protein. So what exactly have we done? We took very sophisticated machinery and technology, simply clone the genes and stick it into the greenhouse. So a new company was established based on this technology called Biobetter, and we've been able to cut the cost of production by 2 orders of magnitude. And we are now going to complete, once we complete the clinical trials, to offer the drug for less than 70 cents a day. So even a farmer in India that makes maybe $8 a day, and for sure cannot afford $100 or even $10 a day, he can afford 70 cents. Okay? Because if he has a Crohn's disease or rheumatoid arthritis, he can continue to work, and he doesn't need the government. Trees. Trees have always been exciting for me, particularly sequoia trees. You know, they're huge. They carry hundreds of tons for hundreds of years. In cold weather, hot weather, UV light. In fact, I'm not familiar with any plastic chair that can survive such harsh conditions. Yet, if you ask yourself, how come that these trees are so strong? So if you look by high-resolution electron microscope into the structure of this tree, all of a sudden you find out that it is actually made of nanofibers, about 100 nanometer in length and about 5 nanometer in width, extremely, extremely strong, yet it's made of sugar. Well, not exactly the same sugar we drink in our tea. It's not sucrose. It's actually a homopolymer of glucose, which is called cellulose. But it's not a regular cellulose. It actually highly crystalline form of cellulose chains that makes this material so strong. In fact, it is so strong that on a weight basis, it's about 10 times stronger than steel, and yet it's made of sugar. So analysts all over the world are really excited about this material, this nanocellulose. I was happy to learn that you're also working on bacterial nanocellulose here in university. And they're really excited about it because they claim that nanocellulose is going to be one of the most important nanomaterial for the entire industry. So not just transportation, aerospace, but food and medicine and almost anything that we will touch in, from 20-something, will have a little bit of nanocellulose. But here's the problem. Say 7 years ago you wanted to buy half a ton of nanocellulose because you wanted to build a boat or an airplane. You could Google, you could eBay, you could Alibaba. You couldn't find it. I mean, you would find thousands of papers coming from scientists like myself and others all over the world saying how this is a great material. But there was no commercial source. So we at the Hebrew University, together with partners from Sweden, Italy, Germany, and Finland in one of the six-frame projects, we actually decided to focus on developing a cost-effective method to produce nanocellulose and develop different applications. So the first thing we were looking for is a source of raw material. Obviously, we didn't want to cut sequoia trees, but there is no reason because cellulose is everywhere. And in fact, we identified one very good source, and that's the sludge of the recycled paper industry. Well, one reason why it's a good source is because there is a lot of it. In fact, we have so much of that, it practically covers our continent. Europe alone produces 11 million tons of that sludge annually. Just to give you a feel, this is a mountain, about 3 kilometers high, sitting on a soccer field. No ski resort. And it's not just Europe make it. The Americans make one mountain, the Chinese probably few mountains every year. So for everybody, it's an environmental problem. For us, it's a great source of raw material. So the technology was actually developed by the Hebrew University together with our Swedish partner, and a company was established called Melodia. And today, Melodia has already 2 sites, one in Israel, one in Sweden. We're now building another site in Israel up to 200 tons per annum. And we can now make a lot of nanocellulose. So the question is, what can you do with that? Well, a lot of things. One interesting feature of nanocellulose is the fact that once you put it in water, suspend it in water, and the concentration is above 2.5 or 3%, all of a sudden it makes liquid crystals. Now these liquid crystals, once applied on any surface, and it can be paper or plastic or concrete, once the water evaporates, it self-assembles into an extremely strong and transparent film. Now this film is so strong, it is 2 times stronger than epoxy resin. And remember, there is no covalent bond. It's only hydrogen interactions, van der Waals interactions. So simply the fact that these fibers are so well organized ones next to the other. So one interesting application we developed was to strengthen cotton yarn, the same that my shirt is made of. So we have shown that by coating with the nanocellulose, the cotton yarn, only increasing the strength, the weight by 1%, we've been able to increase the toughness by 500%, which means that now I can make the same shirt with 1/5 of the material, or maybe make the shirt for Superman. Another interesting feature of a nanocellulose is that by itself, it's an excellent oxygen barrier. In addition, by mixing the nanocellulose with another nanoparticle like zinc oxide nanoparticle, we can make films that you can see block effectively the UV while leaving the visible range wide open. So why is it so important for the packaging industry? Because in the old days, you can see on the left-hand side, that's how we used to pack our food, in tin. That's a great way to prevent photooxidation. But it's heavy and expensive. So the flexible packaging industry has been developed. So these are laminates of low-density polyethylene, aluminum, PET, whatever. That's a great product, big industry, $1.5 trillion business, but extremely polluting. Why? Once you laminate aluminum on low-density polyethylene or polypropylene, there's practically no way back. So we are building now an island in the ocean that is probably grow into continent if we don't stop that. What we have shown is that by taking PLA or another biodegradable plastic, we can coat it with nanocellulose, and by doing that, we can totally replace the aluminum. But this is yesterday news. In fact, the future, I believe, is by coating the individual food servings. So in the future, we will coat even the muesli or the cornflakes. And then when we put it in the carton box, we will not even need the laminate at all. Now, admittedly, at this point of time, nanocellulose is not approved yet in Europe and the US as a food. In Japan, it is already. In fact, I was there in June, and I had the chance to eat biscuits made of nanocellulose. So soon, it probably will be. Another interesting thing you could do with nanocellulose is 3D printing. So you can see here, because it has an extremely nice thixotrophic properties, you can print water basically at room temperature. And look what happened once the water evaporates, it self-assembles into fibrous texture. That becomes relevant to the next topic I would like to share with you, and that is 4D printing of meat replacements. So you probably ask yourself, well, we know what is 3D printing, so what is the fourth dimension? So hold on, I'll let you know in a second. But first, let's talk about the problem. The problem of the animal agriculture industry is that it is extremely polluting industry. In fact, we are using for that about 30% of the good land, 25% of the good water. In terms of greenhouse gases, where this industry makes more than the cars, the trains, the trucks, the ships, airplanes together. So there's no way we can continue with that. This is not sustainable. And I'm a carnivore. On the other hand, there are market trends. So people would like now to have more organic food, less carbohydrates, more proteins, and so on. And there are more vegetarians, more vegans. But in fact, the most interesting population are the flexitarians. Flexitarians are those people that are carnivores. They like steak, they would like burgers, but because of environmental issues and health, because they don't want the antibiotics, whatever comes with the meat, they are ready to eat once or twice a week a veggie burger, or hopefully in the future, a veggie steak. And there is another trend, and that's the personalization. Now, the industry actually started to move into those directions, so you're all familiar with the Beyond Meat and Impossible Foods. But, you know, if you don't like this product, you don't really have an option. 3D printing is a way to personalize things, and the industry moved into that. So now people are printing chocolate. Well, chocolate tastes good, but it's not really food. Sorry to say it in Switzerland. I love chocolate. They print pizza. They print pasta. But then you need to take it and cook it. So we decided to take the next step and use the nanocellulose as a binder on one hand, which has 0 caloric value. It's actually a prebiotic fiber. It gives you all the textures for all the way from gelatinous to fibrous and even hard as a bone. So theoretically, in the future, we'll be able to print a T-bone steak. And we wanted to add the next stage, and that's the cooking. So we developed a special head that enabled us to print a layer and cook a layer. And the cooking is actually done by relatively high resolution. So that enables us to determine on the three-dimensional space if we want to bake or fry or grill. So this is actually the fourth dimension, this gastronomic sensation. So all of a sudden, we now have the ability to print and cook something like burger that is not just crispy from the outside, it can be crispy also in the inside. Now, how do I see the future? The future will be you're sitting in the hall, you know, the 15 minutes, so that will finish his, probably less, his lecture, and I'm hungry, I'd like to have a burger. So you open your application, you select Savor It, that's the name of the company, and you look for the burger that you like. But here's the thing. You can now decide if you want it thick or thin, chunky or more minced. You can decide if you want 18% fat or only 2% fat or 3% fat. And you would like it to be well done or medium rare, and you push it, and 5 minutes later, it will be in the kitchenette next door to you. Insects. Insects are great. In fact, the wonders didn't stop in the plant kingdom. Every kingdom gave us some really wonderful things. And I'm attracted to this creature, the cat fleas, for the last 12 years. I'm in love with cat fleas for a simple reason. They are world champions in jumping. They jump about 100 to 200 times their height, which is quite amazing if you consider that, because it's the equivalent of a person standing in the middle of Manhattan and in a single jump go to the top of the Empire State Building. So everybody would like to do that. The question is how cat fleas do it. So it turns out that during evolution, they developed this very special protein which is called resilin. Resilin, in simple words, is the best rubber on earth. You can stretch it, you can squish it, and it doesn't lose almost any energy to the environment by heat or friction. And it can store the energy for a very long time. Once you release it, boom, it brings back all the energy. So the cat fleas make their jumping pad made of their material. So they store the energy, and they release it, and boom, they can fly up in the air. So everybody would like to have resilin, so one way is to collect cat fleas. Bad idea. Why? Because they're jumpy, not very easy to catch. But that's where technology comes into play, because all you need is to catch one, and then extract the DNA, clone the gene that encodes for the resilin, and introduce it into a less jumpy organism, like a plant or bacteria. So that's exactly what we did. In fact, we made another trick, because I didn't tell you everything, but in the cat fleas, it's actually a nanocomposite made of nanofibers of chitin and the resilin protein. So the resilin protein has a chitin binding domain. So we prefer nanocellulose for all the good reasons. So we replaced the chitin binding domain with the cellulose binding domain. So now we have the opportunity to make nanocomposite of resilin and nanocellulose. So we asked ourselves, what will going to happen if now we'll make a cellulose foam with or without resilin? Will it affect its mechanical properties? So you can see now this short video. You can see on the right-hand side, it's a cellulose foam, nanocellulose foam in water. I squish it, and you can see it has only plastic behavior, so it doesn't come back. On the left-hand side, it's exactly the same foam, but also now with resilin. So look what happened. So you can do it again and again. By the way, I found out something very, very nice. Whenever I get to this picture, everybody starts to laugh. I think it reminds us of our childhood. Either Humpty Dumpty, or in Israel we have something called Nahum Takum. So every society has this thing, and it reminds us. So there are a lot of things you can do with this material. This is one thing we're doing. We're working with a Swiss company to develop the next generation of sports shoes that will have resilin nanocellulose in the midsole. So the idea is for athletes that will have better performance using the same energy. Now, you remember the collagen fibers I told you. So we asked ourselves, what's going to happen if we will add 5% resin to these collagen fibers. So this is what happened. In fact, we've been able to generate fibers that are about 380% more tough and 300% increase in the strain it breaks. So oddly enough, in the future, once we will make artificial tendons from that material, the patient will have better performance after the surgery than he had before the injury. So what's for the future? I believe that in the future, we will be able to produce almost anything in plants. So not just collagen or resin that comes from insects or from human. In fact, we can make everything that nature gave us. And then purify these materials, and using modern technologies like 3D printing or additive manufacturing technologies, we will be able even to make a heart. Now, admittedly, heart is difficult, but once we make it, it's not going to be as good as we can get from a donor. It will be better because we are going to use better materials. So again, this is not for now. It's going to take some time because heart is really, really complex. But I can tell you that we actually developed recently at CoPlant metacrylated collagen that now can be used to print tissues. And we have a program together with United Therapeutics, that's an American company, in 3D Systems, using our BioInk and 3D Systems bioprinter technology and United Therapeutics stem cell technology and bioreactors. We are now engaged with the program to print the first human lung. Now, this is not something for 10 years from now. In fact, our plans are 4 years from now, first in man. And I would like to summarize my talk today by quoting Pavlov, because I think Pavlov said something really smart. He said that if you like a new idea, you should open an old book. And I say that the book was written. The book was written over billions of years of evolution. And the text is the DNA of life. All we have to do is read this text and start our progress from there. Thank you.
Oded, fantastic. I'm quite sure that many of you want to ask questions to Oded already. May I just ask you for a bit of patience so that we can have 3 short presentation in between, and then we'll do all the questions all together. Is that fine? Okay with you? We do it this time? Okay. Now it's my pleasure to actually ask, we go to the next one. Dr. Ribordi, actually from ID Quantique, who will give us like an idea of what innovation can happen in Geneva as well. Okay, sorry. Thank you.
Thank you very much. Good evening, ladies and gentlemen. It's a pleasure for me to be here tonight. So we just heard that opening an old book is a good way to find new ideas, and what I'm going to tell you is a little bit similar. We're going to see how opening the book of quantum mechanics actually can have an impact on information technologies. Quantum mechanics is essentially, the science, the physics of the early 20th century, which was developed to describe microscopic systems. And for a long time, physicists saw quantum mechanics as an interesting theory that could lead to very good, very precise experiments, but with very little applications. And in the mid-'80s, some physicists started to think, well, what if we tried to apply the special principle of quantum mechanics to do something that is not possible with classical physics? And of course, in information technology, devices were becoming smaller and smaller, and so when you make a processor smaller, at some point you get closer to the size that are used, that are described by quantum mechanics. This led to quantum computing, and some of you may have heard recently that Google made a big announcement claiming that they've built a quantum computer that reaches quantum supremacy, which it means that it would be more powerful than the most powerful classical computer. So that's one application of quantum technologies in the field of information technology. But there's also another application, which is to secure communication. And it's actually very important because quantum computing can actually bring some challenges. It can break the cryptography, the coding technologies that we're using nowadays to secure communication. Every time you go on the internet to do some e-banking, you connect to your bank server and you see this little HTTPS text. It means that the information is encrypted using some mathematical techniques. And the security of these coding or this cryptography comes from the fact that it is difficult to solve some mathematical problems, that there's not enough computing power to solve these problems. Now, with quantum computing, if someone can build a big enough quantum computer, these mathematical problems become simple, which means that an adversary can break all the codes. That's a problem, maybe not for today, but it's a problem that will come once quantum computing continues to advance. And there's a way to protect against this, which is also by using quantum physics. And that's something that was developed at the University of Geneva in the group of applied physics. In the mid-90s, physicists started to experiment with single photon communication. Essentially, optical communication used light in optical fibers. Now, if you send very weak pulses of light, one light particle, one photon, physicists call these photons, one at a time, you send them across optical fibers, you will actually be able to notice if someone intercepts these communication. A photon is a quantum object, and in quantum physics, if you measure something, you perturb it. This is the well-known Heisenberg uncertainty principle. And so you can use this principle to detect interception of communication on an optical fiber, and so develop systems that enable ultra-secure communications. This is something that was first demonstrated at the University of Geneva. The theoretical idea doesn't come from the university. It was invented in the mid-80s by researchers at IBM and the University of Montreal, but it remains like something interesting but not really applicable. And in the mid-90s, the group of Professor Giza, who was doing research in the field of optical communication, optical fiber, traditional communication, they read an article in Scientific American where the idea of quantum cryptography, quantum communication was presented, and they said, well, we could try to do it. We have everything in the lab. Let's try to build a little experiment and see if it works. And so in the mid-90s, there was a first PhD thesis on this field. They demonstrated that this works, did that even over an optical fiber between Geneva and Nyon under Lake Geneva, which generated a lot of publicity. And since the technology worked, the idea was to make it more stable, build a system, go from a tabletop demonstration to a real system. And so by the end of the 90s, the university had developed a nice prototype, and that's when ID Quantique was founded in 2001 with the vision to bring this technology to real-world application, to do the last step, from prototype to industrialization, to something which didn't require a couple of PhDs in physics to run, but could be handed over to an IT engineer and could be used for that. And so ID Quantique was founded with this vision of bringing this kind of technologies to the market. And we were able, after a couple of years of work, to do the first application, demonstrate the first application of quantum cryptography, actually in the context of the IT system used for the federal elections. We just had federal elections. Well, in 2007, the federal elections in Geneva were secured with this quantum cryptography technology, and it was a world premiere in terms of deploying this kind of technologies. Now, ID Quantique continued to develop. We're based in Carouge. We have about 110 employees, and we are the world leaders in this field with customers in various sectors, finance sectors, government, industrial sector, organizations that need high security for communications. Maybe one thing that I'd like to say before I finish is that very often people link innovation and risk. And very often people say, well, with innovation, you take a big risk. And I must say myself, I never saw innovation as a risk. When you're 30 years old, you start a company, what's the risk? You can always try. If you fail, it doesn't matter. The next time you'll fail better, and you will learn a lot. I think now, though, that there is a link between innovation and risk. And for me, where I saw this kind of link is with customers. When you try to sell something to a large corporation with people that have to run a very critical infrastructure, you go and talk to them about quantum technologies. You say, it's cool, it's innovation, you should try to do that. And all they see is risk. The system is stable, it's working. Why put something else, in the system? And so that's where I think there's a link between innovation and risk. Now, it's interesting, Professor Lacour talked about fundamental research. When IDQ was founded, the technology we were working on were the most fundamental research done at the group of applied physics at the University of Geneva. They were doing some very applied stuff in optical communication, sensing, but quantum was really the most fundamental thing. 10 years later, well, they were still doing quantum cryptography, quantum communication, but it was the applied part of their research that moved on to other fields, other research, which were much more fundamental. And now sometimes when we chat, when we collaborate with them and discuss, they sometimes say, well, what you do, you guys, it's too applied for university. We can't really do that anymore. It's too applied. So it's interesting to see this cycle over 20 years. Now, maybe as a final note, the technology that we developed for this telecommunication system, the most difficult part is a sensor, is to detect light, at a single photon level. And it's interesting, but we've found another application for this technology in an instrument that will be used by the European Space Agency to test the ignition system of the Ariane 6 rocket, which will launch about a year from now. And so the day this rocket will be launched, one of the green lights, in the control room in Kourou will come from an instrument and a technology which was developed for quantum communication, but it has very different application. And so it's very important to always keep an open eye, open mind for other applications of the technology that you develop. Thank you for your attention.
Thank you, Grégoire. Wonderful. I mean, this is already like a feast. Oded, Grégoire. Now we're turning to Eric. Eric is a professor at the New School of Pharmacy called ISPSO. I still have trouble saying it. Eric, please, you're the founder of Kyle. You're the best one.
Hello. So the slides are those ones? No. Okay. So it's really great to be here tonight. And just in a few minutes, I would like to tackle the word of curiosity. Out of your own box leads to patents and possibly entrepreneurship. So I'm a pharmacist by training, and I had a PhD here at University of Geneva, went for a postdoc, worked a lot in nanoparticles and materials like polylactic acid you mentioned. And then for a few years, I worked in the company Bracco and heading a research group working on microbubbles for ultrasound imaging. And then I came back to university as professor and recently co-founder of a startup company. If I'm talking to people here at university, I think one of the tasks is to do at the same time, reading, thinking, working at the bench, writing papers, nice papers, famous papers, of course, and maybe file patent applications. Why? If you are going to work in different environment than university, of course, scientific papers are interesting, but when you go for an interview, people are telling you or asking you, did you find some patents in your life? And this may be important. And I thought that tonight there would be more PhD students and master students here in the room, but I would say that less than 5% of the person reading the slide, if this were PhD student, would stay at university. So I think patents are quite important, not only for that, of course, for other things. if you want to keep in mind only one thing from my talk, I think it's this picture, right? This picture, I think, is really the symbol of curiosity, novelty, inventiveness, and what we call no limit attitude, just going across barriers. And I think as an adult, I want to stay a little bit like a kid, and then it's quite useful in your life. So patents reflect curiosity, novelty, and maybe you will translate ideas to products and uses, because the society needs that. So just 4 examples of application I had during my life. That's quite old now, 95. So nanoparticles that contain a drug, and once you deliver these particles to organism, then you put some light on it, then you have toxic reactions. And so we filed that patent in collaboration with Supervision in QLT, and the product was quite good to treat macular degeneration of the eye, which is quite frequent. Unfortunately, we were a bit late, and then the liposomes were sold, not for a long time, but I think our product was quite good. Anyway, when you go for patents, you are not always successful. What I wanted to tell also is I think it's good not to stay in my own box of a pharmacist, specialist of nanoparticles, but maybe think of other application. Why not agro-food? We had some nice examples before. When you eat a cabbage that you have bought in the market, this cabbage has been sprayed about 17 times with pesticides during 4 months of growth, right? Why not reducing that? So the patent was quite simple. You put one seed, some pesticides, you take a capsule, you put all of that inside, you put some cellulose inside also, and you get one single thing, and this was an invention that reduced the amount of pesticide of about 17-fold, less pollution, of course, and more efficient agriculture. And it looks like a drug, but it's not a drug, it's something for the agro-business. When I went to Bracco, then I was thinking about microbubbles. Microbubbles are things that you build and that you can then inject to humans. And when you use ultrasound, okay, ultrasound imaging, you see really a lot better vessels, blood vessels, where you have those microbubbles. So I worked for 8 years on microbubbles, and I was taking breaks with physicists, acousticians, and then we were thinking, how could we help medical doctors, radiologists, to do diagnosis of the liver, for instance. And we came to that patent, auto-scaling of parametric images. Of course, we do not understand anything when reading the title of that patent. What it is right now, it's something called ViewBox from Bracco. And actually, in the liver, those microbubbles that you inject, they can come to a lesion and then leave this lesion in different patterns. And the different patterns are those 4 patterns. And from those 4 kinetic patterns, you can diagnose, for instance, hypervascular metastasis or hepatocellular carcinoma or hemangioma. And a radiologist, when he had the patient, he wants to give the answer or say immediately what is happening. So in real time, you need to do the diagnosis. And actually, the pattern is just having these kinetics and translating that to color codes, like the green one, the red one, the blue one, the yellow one, and you can tell your patient that it's either a bad situation or not so bad situation. And this was really, when I come back to that, just because I was next to my colleagues, physicists, and they were more thinking about those nice curves going up and down and down and up. And I told them, just make it simple, make it a color code, and you will have a nice tool. So we did that together, and we came to that ViewBox. Fourth example, more recent now, as professor at University of Geneva, I had a PhD student working on those hyaluronic acid polymers, and I was asking him to do something more viscous because I thought more viscous was good. And once he came to the lab and he said, well, it's not working. It's not more viscous, but it produces some little tiny things, those tiny things here, nanoparticles made of hyaluronic acid, and said, well, didn't work. And said, okay, it didn't work, but maybe it's useful. And we filed a patent. And this is quite useful because hyaluronic acid is injected in the knees of people suffering from osteoarthritis. And unfortunately, it does not last long in your body. Actually, you have the polymer on the upper panel, and you have those green Pac-Man. Those are enzymes that we have in our body. So when we get an injection, after a few days, you don't have your hyaluronic acid anymore because this polymer is endogenous and recognized by enzymes. With our product now, we have those little spheres, and the enzyme cannot crush them. So, filed the patent with the help of Unitech, of course, and then 3 years ago went to the hospital for some how we call Prix de l'Innovation. And actually we got the first prize and also a Fongite Eclosion prize. And then we incorporated a company. We went in different places, and now we entered the national phases with our patent. So the story is continuing. I think it's a very nice adventure that I'm just trying to run at the same time as my duties of professor and also president of the School of Pharmacy. So just the take-home message, I think, for these 4 examples of patent application, always curiosity, and I'm just asking my PhD student to really push this on curiosity, not doing something that people have done previously. Also think out of the box, of my box of expertise, because maybe pharmaceutical science is useful for other fields of industry. Interact, of course, network. Why not drink coffee, and maybe not only coffee? And think about nice publication at university, because we need that, but not only publication, nice patent application, and keep in mind this, this nice picture. So I will end for that, because I had only, I think, 5 minutes. And of course, I'm open to questions later on. And if anybody wants to invest in Kilis, I'm ready for discussion.
I think you two guys should talk to each other. I see a lot of future between Jerusalem and Geneva in some application, maybe directly between the two of you. Now it's time to welcome Jean-Pierre Wolf. He has the title just Physics. I love it. Okay, Jean-Pierre, this is true.
Well, I hope I will not disappoint you. It's not all physics that we are talking about, but our group was or is still very interested in the application of lasers. And you may recognize one guy nearby the Berlin Wall on the left side. I hope you recognize the guy, because otherwise I will be really sad that nobody recognizes me anymore. But it was in 1989, and I'm sure you are asking yourself whether the wall fell because of the laser in the in this box. It was not the case, unfortunately. But we were working there and measuring pollution, actually the importation of pollution from East Berlin to West Berlin at that time. And so we went on with this fascination of lasers. I'm sure you heard at school that the laser has a very pure color. That's one of the best characteristic of a laser. Just next to it, it's a white light laser. So you can also have white light lasers, which is quite interesting. For instance, the Nobel Prize last year was about this topic. Unfortunately not in Geneva, sorry, Jérôme. And then about air pollution, we were also very interested by small particles in the air. And we developed also laser-based system to measure pollution, pollens, spores. And here on this nice solar boat, Planète Solar, we measured the aerosol emitted by the ocean. Another application that we like for the atmosphere is not only measuring, but also trying to control atmospheric processes. And the atmospheric processes like lightning control. So as you see here, you can direct high voltage discharge along a laser path. And we have now a big project together with important industrial partners, as you can see here, like Ariane, to divert lightning from launching pads. The other activities about laser applications that we have are more on the nanobio side. Here on the left side, you see the use of nanoparticles which emits harmonics in order to measure the development and look at development of stem cells, cardiac stem cells or neuronal stem cells as here. We use also these harmonic nanoparticles for theranostics, so something similar that Eric just presented, but with another approach. And recently we developed also nanothermometer, and the aim of it, of which is to measure inside the cell locally the temperature near a mitochondria or near the nucleus or something like that. But all these applications, of course, are closely linked to tech transfers. That's also why I'm here tonight. So from our group, several startups were founded, Elite in Berlin and Dilex, and also Lysel, and more recently Blair. They all stem from our group. And also on the tech transfer side, we have a lot of collaborations like Airbus or Ariane or Thales, but also Swatch or Coherent and Nikon and BD. And as Eric said, also with some international patents. What is important is that for all these tech transfer activities, it's very important to have reliable and very active services for the tech transfer, and it's the case here with Unitech, as we heard tonight, but also the Geneva Creativity Center, and of course now the Science Innovation Hub, which we will visit a little later. So at the Innovation Hub, we have started a new project. As I told you, we are interested to measure, analyze, identify particles in air. And so one thing which is especially attractive is to measure some pathogens in agriculture, some kind of early warning. And the idea is again to use lasers to measure the pathogens while they are really propagating in air, not already active on the plant, but before. And so basically the aim is to measure, and very early, measure the presence of these pathogens like mildew, powdery or downy mildew in the case of vineyards. And to really treat the plants at the location, so where and when it's really required, when it's really needed, and in order to reduce the load in pesticides in these fields. And so we developed a concept based on a network, and we treated, we applied it in a famous vineyard in Dardanie in Geneva. I'm sure if we have an aperitif afterwards, we may have some wine from them. And so the idea was really to use airborne laser system to measure airborne particles, which can be either me-scattering from a laser or digital holography, to identify what kind of spores is present in the air. The stations are standalone, as you see here. They are real-time, automated, and they discuss via 4G. And the idea was to spread our stations around in this field. It's 65 hectares. And then look at the presence of spores and the environmental conditions which are favorable or unfavorable for growing these illness, this sickness. And this is a typical example. So we measured not only the spores, but also the environmental data like temperature, humidity, leaf humidity, moisture on the soil, and so on. And we used all these data for analyzing patterns, which are representative of very urgent and soon infection. And as you can see from these pictures, when it's red, it means that the occurrence is very high. And at some certain location, you have a big square, red, means that you have the pathogens at that location and they can correlate with the environmental data. You have to do something with your treatment. And at some different places, you don't have them and you should just forget it. And of course, it will also prevent further spread. That's the idea. So if you are interested, you are welcome to visit us at the hub in about 10 or 15 minutes from now. And I thank you for your attention.
So thank you, Jean-Pierre. So you could see we had a really like series of serial entrepreneurs here and academics together. This is great. And now it's time for me to introduce actually someone who is going to moderate the table ronde, who's actually, he was mentioned several times through his organization Unitech. This is the Yisum of Geneva. So I think we should say, this is maybe the new way to present actually Unitech. No, sorry. Okay, Laurent, the floor is yours.
Thank you very much, Jérôme. Please, all the speakers, can you just join me on the podium here? So my name is Laurent Miéville. I'm the head of the Technology Transfer Office. Yes, Oded, please come join us. I won't spend time talking about the Technology Transfer Office. I think you've seen examples of technology transfer. I think that's enough for you to understand what we do. I have to say these four gentlemen are very important to technology transfer. And Oded, I'm sure you are very important to your university as well, but they've produced very high-level inventions and technologies and innovation. And thanks to them, and also to Jérôme and people here at the Faculty of Science, I've done 20 years of very interesting job because I had to review such very interesting disclosures. So thank you very much for all you've done, and I think they can already get applause for that. So now I have a challenge because I was supposed to end now the discussion. And I know you guys would like to visit the Science Innovation Hub. So I will be a bit shorter as scheduled. So you have time to ask a few questions and then also to visit the hub and have a nice aperitif with some wine. So I'll start with some question already. Maybe Oded, since you gave us this very inspiring talk. What was the trigger in your scientific life to start doing the innovation part? What made you transform from a researcher to an innovator?
So I'll try to keep it short because it's a long story.
In 1 minute.
So I was a young faculty member, and at a certain point of time, I met a professor from the Weizmann Institute who was already quite experienced, and he asked me to become a consultant of his startup company. So I get a phone call from the Weizmann Institute, and they tell me that they would like me to be consultant of Professor Yaron Cohen, who was a very famous immunologist at the time. And so they said, would you like to be a consultant? I said, okay, how much I need to pay? He said, no, we're going to pay you. I said, well, that's even better. To make a long story short, I became a consultant. One day, I find myself going to Japan to identify a particular molecule for them. I come back, and the CEO would like to meet me because it was a very successful trip, and I was able to identify the molecule they wanted. And so he asked me, what are you doing there at the Faculty of Agriculture? What kind of research are you doing? So I told him that I'm working on a protein called cellulose binding domain. And he says, oh, so what can you do with that? I said, oh, cellulose is everywhere. Everything, almost everything is made of cellulose. So simply the fact that you can bind things specifically to cellulose can be very interesting. So he said, did you file for patent? I said, no, I'm not interested in patents. I just have a paper going to be published in PNAS. I have the galley proof already. He said, but doesn't matter. First file for patent, then you can get your paper published. I said, no, I'm not interested in patents. I need publications to get my tenure. So he said, okay. He calls a guy that said, can you give me the phone? I said, he called ISUM, the technology transfer, and said, listen, I have here a young scientist that he doesn't
come
want.
right away to write a patent?
Yeah. So he said, what do you want me to do? He said, listen, I'm going to do a deal with you. I'm going to give him $150,000 for 2 years to make a proof of concept. If it's successful, then we are going to establish a company. I'm going to give him 4% equity, and what I want you to do is to give me a fair deal, because I don't have time. I'm going to take his the publication and send it to my patent offices, so they will file a patent before it lapses. So the guy from the other side said, well, I want to talk to him. So I take the phone and he said, did you understand what he said? I said, almost everything. He said, what's the part that you didn't understand? I said, I don't know what is equity, but I know I'm getting it, so it's probably good. So that was the first company that we established. The company was sold for $100 million years later. So I had a good experience.
All right, so I think it's very inspiring to see that you were able to have a very good start and really be successful. So yes, I hope we can do the same with the people that come to Unitech and make on a very short decision kind of moment and be successful afterwards. I have a question now to Grégoire. I remember a few years ago you were giving a lecture to young students interested in entrepreneurship, and that was really the start of Idée Quantique. And you said, don't do business plan. Business plan is really nothing interesting. You should just go ahead and do your stuff and create your company. Don't spend time writing long business models and filling up Excel sheets with numbers. Just do it. Do you still believe in this kind of advice now, or did
I say that?
Yeah.
Because I have done a few business plans, I must say. But of course, when you start a company, most cases you're running a marathon. In the case of Idée Quantique Deep Tech, starting in the early 2000s with quantum communications, it was really difficult to see how we would really make money, be successful. And so the first business plan we wrote was really wishful thinking and didn't bear too many, wasn't that relevant. So I think it's useful to write business plans still. It's useful to identify assumptions, that are important in the business you wanna build, but at the same time, don't believe too much in your business plans, and spend more time trying to implement things and to try to do things instead of hide behind an Excel sheet.
All right, so you still believe in what you said. That's good. Eric, I understand that you've been working on many technologies, and now you are really into the startup kind of aspect of it with Kilis. And what's your most challenging element in your entrepreneurship startup venture right now? What is the thing that is requiring most of your efforts to get through? I understand financing seems to be the questions on the table right now. Is that correct?
Well, not only. I think as a professor and having ideas and finding patents, you get to the issue of not having enough time to do whatever you want to do. And right now, running the company and being professor and all the other duties is quite challenging. And we just want, for a little period of time, to give more value to the company, do additional work, and then go for financing. So it's kind of a critical phase where you put your own money in national phases for the patent. And because we want to cover a big part of the world, well, it costs some money. So we're in that critical period, needing some additional time and, well, fighting for that.
Yeah, I see Jean-Pierre was smiling too, because I think this is something you experience also with all the collaboration, the technologies, the ongoing projects. I remember we had long discussion about, you know, the role of a professor compared to the role of a PhD that is trying to get a company starting. So what's your take in all these projects? How can you manage all in parallel and still being successful in your research and innovation project? I know you also got a lot of support from many very important grants that you have to write up and defend. So how do you manage all this in the same kind of person?
I think the answer was in Eric's talk. Is the little kid, you know, who was like this. So I think I still have this part in me, and so I'm very enthusiastic. And this actually drives you. I got my kids really pretty late. Some people say that it's not true, but and it keeps you young, and it's about the same thing. You know, if you keep this mind of a kid and interested by new things, and then you realize after a while I shouldn't have said yes to this, but okay, I did it, and it's nice. And I think that's the drive. The drive is to keep this kind of very open-minded way of thinking, and also this enthusiasm for new things.
Curiosity-driven person, yeah.
Yes.
All right, now I'm gonna open up the floor for questions. Now Gerrit is raising his hand very quickly. He just got an innovation prize 2 weeks ago, so
It wasn't me. It was
congratulations.
my postdoc, actually. Thank you very much. All nice talks. My question goes to Oded. Just a technical question. I mean, finding the right name for your company is a very decisive step in this process, right? And if I look at this name, BioBetter, I couldn't help but wonder whether once you start or have started talking to the FDA, you would go for the 351K biosimilar pathway of approval. And if so, as a biosimilar of your antibody, and if so, if you're confident to beat the cost of goods for the other biosimilars that are already on the market, which are already reduced compared to the RLD.
So it's a composed question. Well, BioBetter, I was actually surprised that the name BioBetter was open. It wasn't actually me came up with the idea to call it, and it was one of my students, and when he came, I said, there's no way that it's still open, but it was. So we use this name. I don't think that the FDA is going to give me any benefits for that. So we will have to go through all the regular, normal biosimilar. We decided not to go first to the US. And the reason for that is because when we started our investigation, we realized that in the US, most probably because of the strong lobby of the pharmaceutical companies, we will need at least 1,200 patients. Whereas every normal statistician will tell you that 300, 400 patients is enough, at least for one indication like rheumatoid arthritis. So we actually decided on a totally different business plan because obviously as a startup company, you don't have money, you don't have the hundreds of millions of dollars to do it, even not tens of millions of dollars. So we defined ourselves as a seed company and not as a pharmaceutical company. We do tech transfer. So what we're doing, we are collaborating or signing agreements with pharmaceutical companies in different territories. So we have now already established with a Russian pharmaceutical company, and we're now conducting a preclinical and clinical trial in Russia for the Russian market. Obviously, it will be good for Russia and not for anybody else, because I guess not too many, unfortunately, or fortunately, I don't know, rely on the Russian regulatory authorities. But we are going to do the same with other territories, and hopefully at the end we'll do it also in the US, because US is still a very big market.
Another question there. There are microphones on both sides, so if you just raise your hand, then somebody will come with a microphone.
Yeah, thank you very much for these very inspiring talks. Also, from the comments from Laurent, the question is there really a need that the scientist is involved in all the steps for the company, or is he wasting his time with this?
I'm ready to take it. I think that from my personal experience, at least for me, it would have been a big mistake to become a CEO. You need to come to my office and understand that I'm a very bad manager. So I always do two things. First of all, I don't take any executive role, so I will not be even VP R&D. I'll be chief scientist, something like that, because I believe that in a startup, all the employees have to wake up in the morning, go to sleep with the startup problems. And obviously, we have other things to do, and we're not qualified to do that.
I think James had one question, and then we take one more to give enough time for you to visit then the Science Hub, and also to Jérôme to do the concluding remarks.
So I'm always interested in the relative importance of patents and publications in an academic setting. So imagine you were going to recruit a new faculty member, and one has a certain number of patents, pure publications, another one has a mix of patents and publications, and you want to decide who should you recruit on the basis. How do you weight the value of a patent compared to a publication?
I think it depends probably on the field, right? So in physics, the people don't look at patents at all. So they look mostly on track records, so kind of publication, in which journal, what is the impact in the community, and invited talks and all these kind of things. But I mean, it depends, of course, on the specific job. But in physics, we have trouble at the moment, really, not to fail in this number problem, where you just look at the publication list and the number of Nature and Science and so on. But it's still one of the measures you have. So the number of publications, the number of citations, and the visibility through via the invited talks and things like that. I mean, if I can imagine that in some other fields it's completely different, but in physics it's like that.
Okay, one last question. Anybody? If not, I just want to conclude by saying that, and Jérôme, remember, we were both in Israel in a small van heading to Institute Weizmann and to visit over there the YEDA Technology Transfer Office, and from this became also a long-lasting relationship between me and the director of YEDA and also the director of Stanford University Technology Transfer Office. And for those of you who are interested in more the technology transfer process, I left a few exemplars of the paper that we co-wrote, YEDA, University of Geneva and Stanford OTL, about the process of technology transfer. And I think it was also very enlightening to see all the common points between Israel and Switzerland. And I think there is a very interesting path to take to learn from each other. And I would like also to thank you, Oded, to be here and also all the organization that brought you here, because I think it's a very interesting field. Innovation, and Switzerland and Israel are very high in the ranking. And I give the word to Jérôme for the visit of, I guess, Science Hub.
But before that, can you just stay a minute, the four of you, because okay. So what did we hear? We heard about plant age, laser age, communication age, nano and not so nano technological age. Okay, all moving together for the innovation age, I would say. We heard about imagining the future, but be on top of the market at the same time, and I really hope we'll be able to do things together to make this for sure, okay? All of us are hearing about personalized medicine, okay? Personalized pharmacy. Now we heard about personalized veggie steak. I mean, seriously, Oded, and this was wonderful. Thank you so much, okay? But basically, the main words we heard was innovation, curiosity, risk, both in fundamental research and applied research. But in any case, I think every one of the speakers said today, we have to keep an open eye. Okay, basically this was also another take-home message from all of you. And what I'd like to summarize, it's with the four of you, I would say, a human touch, a human experience, a human leadership, a human creativity, and what I'm taking out of all of this, a lot of human motivation. Congratulations to the four of you, because you gave me a lot of it for the next days, weeks, and months, okay, following maybe your steps. Okay, really, thank you very much.